Our next speaker is Michael Williams, Principal AI Research Scientist at SLB. Michael will be discussing semantic causality and causal AI, enabling discourse for trust and real-time root cause analysis. Welcome, Michael.
Okay, thank you. So yeah, I'm Mike Williams, and I work for SLB. For people who don't know, SLB is the world's largest supplier of energy services, and energy services is at the end of where energy is created and people own it. For example, an oil company like BP might own an oil field, and their SLB would drill wells, make measurements, and assist essentially in the engineering tasks. The symbol of the SLB is up there in the top corner. The picture shows what the world needs to do for the energy transition. So net zero is in the middle, and the blue curve is the carbon that we will emit, which is far more than needed for 1.5C, and then the carbon that would have to be stored for the rest of the century to meet the original Paris Agreement. So essentially, we look at the world trying to deliver the affordable, secure, sustainable energy. And in terms of causal AI, I'm going to talk about a very practical, how we've practically deployed it. This is how we deploy it today. This is one of those cases that's quite close to the example they gave at the end of when you put AI in a nuclear power station, you better be sure it's safe. The case will be relevant for other industries where you have things that you plan for that you want never to happen. When they happen, you analyze them to make sure that they don't happen again. So they're the most data poor case. In our case, I'm going to talk about what we call stuck pipe. So this is, you want to drill a well, it's 5 kilometers long, 10 kilometers long, it'll have about this diameter. To give you an idea of the engineering challenge of drilling, if you scaled this down to a human hair, so this size scales down to the human hair would be 2 to 3 meters long. The needle would be on the floor over there somewhere, and I'm trying to thread it by spinning the other end between my fingers and thumbs. And that's kind of what a directional driller is doing. And if it gets stuck, you've spent time and days and potentially millions of dollars getting to that point, and now all you have is a hole with a lot of steel in it. So it's incredibly expensive, time-consuming, has all those features of the situation where you would do everything you can to not do it again. So how do we start to look at it? The first thing we do is on the semantic side. So I'll talk first semantic causality, and then the causalLens, causal AI numeric side. We build the smallest, most generic picture we can of the system. So this, you see here, Peter Gregory, he's a big proponent of this approach. This is super generic. So people have talked about time and how do you manage time in different cases. And in general, in the most abstract version, we don't see time. Here, I've got states of the world, activities that get done, and then risk is essentially identified as undesired events. This gets paired with other things that we know. So if you look at the loop around the outside, that's really a state machine. If I've got a world state, it presents some preconditions that could allow activities to happen. Those activities have effects, and they change the world state. And then separately on the right-hand side, you'll see a little box in a rectangle called SOSA. This is sensors and actuators. The nice thing about engineering is there's loads of companies all doing it. So in some areas, like with observations and sensors and actuators, the industries, and this is particularly the automotive industry, have got together and made some definitions. And where definitions exist globally, we'll use the piece that we need. So how do we get this picture, which is essentially going to be able to build any risk model? In terms of timeline, if I'm looking at the climate problem, my activity is I'm burning fossil fuels. The undesired event is I'm going to melt all the ice caps, and that will present as a world of storms and dramatic weather that we don't want. Separately, at the actual drill bit, I might have a little piece of AI that's deciding whether to drill faster or slower. And then the timelines are on the seconds and milliseconds. So essentially the context matters, and we want to be able to instantiate our app for the context that it's given. The way you can apply causality in semantics is almost as simple as it looks. You write out these direction of causality that you're going to enforce. You say these are the only things that you can say. So it's almost now like a language. If I want to do something, I have to define it as one of the 3 classes of nouns. I can only do the kind of 7 different verbs. This gives us an approach called guided authoring. So here's an example, which comes from geology, which I try not to go into too much. But basically, every rock is different. One of the rocks you typically have to drill through to get to a geothermal pay zone, which is a steam-filled crack in a volcanic region, is a layer where there's clay. And anyone who's got clay in their garden will know that when it gets in contact with water, you get a lot of rain, it gets really boggy. So the issue with drilling through clay, which is the paragraph at the bottom here, is that we're using water to lubricate the drilling process. I mean, water with a set of chemicals in it to give it the properties we need. This is going to come past the clay all the time. The clay is going to swell, and over time it's just going to grab hold of the drill pipe, and then it will get stuck. And as I said before, if it gets stuck, that's super expensive. So this is one description of how I could get stuck. The nice thing about this is that the next step, we've done the first 2, people can think later, packing off, is that the undesired event? Or was that a state of the world? Stuck pipe? But essentially you can map from human text into what's called a machine readable form. This is one area where LLMs are pretty useful because you can ask them to take this engineering manual, map it in, and then you can check it because you can say, have you given me cause effect all the way down? You can ask, can I turn this chain into something that a geologist would read? And when the geologist reads it, they can verify it. So this is one way that we use LLMs within the process of building these. But what you end up with is a long line of cause-effect chains that are all essentially declared independently. At the top here, I've called these questions. Again, another good way that we can get data for the final training part is if we set each of these chains with a question at the top. LLMs are pretty good at saying, here's a PDF, here's 10 questions, give me the answers as yes, no, lower, medium, higher, those kind of things. So again, for data capture, it's quite good. The last step in the kind of semantic side of the causality is to build the initial graph. Now, the initial graph has common concepts. So wherever there's a common concept, you just overlay them one on the other. Separately, and particularly in engineering cases like in energy services, you might have chemistry, you might have fluid flow, you might have finite element models of big engineering structures. In those situations, we can run physics simulation models to build a conditional probability table for that particular node. Other nodes will be latent nodes where we don't have any information, and then some nodes are those question nodes at the top. So once we've got an initial graph, we can lay it out. Here is the left to right, but it's essentially the same as the top to bottom that you've seen, where things to the left can cause things progressively to the right. This is where we're now starting to bring in the numerical side. So we've populated the nodes that we can populate from simulations. We've got nodes that we can have questions. Maybe this covers most of the green nodes. Then we do the training step, where we've got those questions and answers, historical data, where we would, call the fit function. But what we find that in addition to causal discovery, where we might be trying to look at how many paths are relevant, we're also trying to look for redundant concepts. Because one of the issues with semantic, and to give you an example, if little bits of rock sink back down to where my drill bit is, they could get stuck. So I could get stuck pipe from sinking cuttings. The normal operation I'm planning for is to flow fluid all the time, lubricating everything, moving the cuttings away. So when I get all the information, I'll have a concept, which we call cuttings transport, of how the design moves the cuttings away. And I'll have another concept from all the times things went wrong, where somebody said, well, the cutting sank, and then the drill bit got stuck. So I need to use analysis of the built graph to find that there are redundant paths, which are essentially carrying identical information. They're either 100% correlated or 100% anti-correlated. And I come back to the expert and I say, you've got these two things, cuttings transport and sinking, and I think they're the same. And that's one element that we have to bring. And on top of that, we use the other kind of causal discovery tools that you have in causaLens. This is a somewhat of an open question right now. So when I said we fit to the historical data, the reality is when you analyze a risk situation, you rarely agree that it was the same issue. And there are many, many reasons why you might consider your risk is high, mostly related to why the mechanism by which you might fail. Now, in our case, we've been able to narrow it down to 3, but this means that when we fit, rather than a straightforward optimization, as in, these are the questions, and the answer is the chances of solids causing pack-off, which is the little bits of stone getting caught around the drill bit, is not the only thing to tune to. And each of these will be different depending on the geometry, where you are in the world, and the kind of well you want to drill. So ideally, we want to bring multi-objective optimization methods to the tuning of our causal AI, because the context in which the person's making the decision determines that sort of fine-tuning element. And if people are working on this, I've been to talk to them, because it's an area where we're at the beginning. The area where we most use kind of the tools similar to causaLens tools is in learning subparts of this graph. So there are various sections of this graph where we can get information from what we call on memory. So it's recorded all the time at the drill bit down hole, but we can't get it to surface. That's because the only communication, there's no radio communication, there's no fiber communication. So the communication is a method called mud pulse, which is literally pulses on the mud. So you can do kind of bits per second. Typical uplink is about 7 or 8 minutes of time. So you don't send information you don't need to send, and you certainly don't send it all the time. It's a little bit like when NASA first went to Mars in the 1970s, the kind of data rates they were playing with and time issues. Oh, thank you very much. But then after the job, we can have high-frequency accelerometer information about all the vibrations. And from that, we can learn, and then that learning, which we can do with the counterfactuals, gets fed back both into the operations side, but also into the decision-making side. So to give you an idea how the fine-tuning works, here I've got green, amber, red, corresponding to extraction of the answers to questions from historical cases where things were fine, things were kind of fine, but we knew what to do, and things where we maybe had non-productive time. And the way we use this right now is we do the calculation on the network. After we've got the calculation, we've got 3 different levels of risk. And what we do is we then use that in the search of the training set, because in real time, this graph you see here, which goes from the low risk to the high risk, gives you a broad picture of where you are, but it's only relevant across the kind of 3 axes. So here, their issue was the center one, which went from low to high, and the other 2 were much more situational. Every well that's drilled in this area has these risks, and we manage them. And so it's about finding what's relevant. Some of this arose out of a comment that one of our clients, early adopters, made, that if they had nothing at all, the only thing they'd want was to be given the report from the people who drilled the last well and a list of what they did, and whether what I'm doing is different, just because historically that's what you would have had. And the goal is to always do better than the decisions people are making today. But that actually led us to a method that's turned out to be very powerful. And in a couple of slides' time, I'll show you how the explanation side of this system work. First, I'll do a recap. So to put together the numerical causal AI approach with the semantic approach, define the smallest piece of your semantic picture that you need. Then your SMEs can attach essentially to the nouns. They're restricted to only say particular types of statement, and you check that those statements are causal. This will overpopulate a causal knowledge graph in that some things will be antonyms, synonyms that you need to discover and help them weed out. And then you want to deploy it in real time. So in real time, this is all about how much time do I have to actually answer the risk question. So this is a behavior tree. Typically we use behavior trees. They're used a lot in robotics. We use them for the automation of the gross tasks. So usually the AI in a behavior tree system is giving you a list of tasks, and they've all got recovery mechanisms and things like that to keep a machine going. So in our case, there's a trigger. Why do I need the risk? Sometimes this is an alarm that comes from a machine learning time series analysis trigger system. Sometimes it's operational, and it can be a formal operational decision. This then chooses the risk I'm interested in. And as I say, normally, if I'm interested in a risk that's stuck pipe, I'm actually interested in 2, 3 different categories of risk, which all combine to lead to the thing. The next step is the planner. So a planner is a goal-oriented task generator. So I've got many things that I can calculate. Even though it's hard to get data from downhole, I've got lots of data at the surface. I'm pumping fluids around. I'm moving the drill pipe up and down. I'm pushing on it. So I've got to choose, in the amount of time I have to make the decision, how to get the most information out of all of those little pieces of AI that I've trained and any kind of causal AI extra nuggets that I've got. And so what the planner does is it says, well, this is the compute you've got. These are all the sensors you brought. These are all the kind of decisions. It's fed the causal network, so it knows which questions could be answered, and it does like an information-led, if I have the answer to this, which question should I ask next? Builds a structure. It executes that plan. This is a decision in the real world, so the reality is not everything's automated. Some things, it turns out, are surprisingly hard to automate, surprisingly straightforward for a human engineer to just go and have a look or take an opinion on. So typically it will pre-populate a questionnaire with some gaps. And if the engineer can fill in the gaps, or if the engineer can recognize some of the questions have been misanswered, and then they'll go ahead and do that. So this is, again, as they were saying actually, usefully in the ethics discussion, putting a human there just before the decision-making part. So then we do the causal network calculation, and it returns the report. And as I say, the report is made half of a report on the current case and the current risk, and then half the set of examples from the training data processed similarly, so people can do a comparison for themselves of exactly where they are. This is a different view of the same thing. If you're people who did computer science or software engineering background will know sequence diagrams. So time basically goes down. Here I've got a team lead, a geologist, and a well engineer. They're representing a whole team of people. And on the right-hand side, I've got the trigger, I've got those autofills, and then the stuck pipe advisor is the causal AI system. And essentially some things, like the geology I'm going to drill through, can be quite well known before time, in advance. So I can be given, if you like, a set of answers to parts of the questionnaire, depending on what you expected to drill in the day. Then at some point, and in this case, this came from the geothermal case, so they drill through, they find steam. As soon as you find steam, the water you're using to lubricate the drill string will flash cool the steam, so it will literally get sucked away. Suddenly you're drilling blind, the cuttings can't be moved to surface because all the water's going away. You need to assess the risk. They get the request for their autofill, the planner gives the execution. Then it goes back to the well engineer, they fill out what they know, then comes in the digital report and the team have an exchange to figure out the mitigation section. So we can't tell them the risk of getting stuck is 70%. They find that no use at all. But what we can do, and this came from Maruna Klinchu at the Heriot-Watt University, so we can give them a flow chart that isolates why their risk happens. In this case, they changed, this is the bottom hole assembly, so this means they pulled all the way out the hole, they put a different bit on, they went all the way back in. And when they did that, they had observations. Firstly, was it tight, difficult to get out of the hole? The caliper is the size of the hole, and that identified that the thing they need to look at right now is the geometry. Now, if I tell somebody, actually, you've changed the size of the bit and your hole's quite sticky to get in and out of, that's more valuable than 70%. So, finally, this is how we build a system. So, I'm happy to answer questions on how the system can be built or how you could build one. But we do have questions. What is the extent to which this approach of teaming the answer with search, how far is that going to get us towards the kind of validation that you really want to verify the safety? Is that okay?
That's perfect. Thank you very much, Michael.
Thanks, everyone.
We have one question, if that's okay. The question is, do you work with AI ML models on the edge or on gateways or in the cloud? Also, do you use causal-AI in acoustic emissions?
So, yes. So we use so we have the system, it's edge. So this is deployed at edge for the well site. But we have what we call well site, town, and cloud as the three categories. Town, we have the real-time center. So that's both, it's not just AI, but it's also physical engineers who have more time and effort to kind of review the process. And then cloud is for big compute, but it's a longer cycle. So essentially we work backwards and forwards. When a decision has to be made at the well site, that's why we have the planner figure out what we can do with the compute and everything like that. That piece is for that edge section, yeah.
Amazing. We have one final question. We can squeeze it in. Did you also apply and combine formal model checking methods?
So formal model checking methods is another talk I'll give on a different day. But yeah, when you want to move AI that you've trained, essentially black box in the cloud, to the edge or to a small device, the general experience is that you won't carry, the training won't carry, because anywhere where the AI has picked close to rounding error values for any weights, then they're ultimately not really copyable. And so there are big issues getting the AI that you've trained deployed on small devices. I love that topic, and I won't say any more now because it's for another day.
Michael, thank you very much.
Thanks.